Take just a couple more minutes, see if I got any emails. Interesting. All right. So whatever you have this pass it down to the then I'll pick them up. Got a couple entries from online and what you all right. So looking through the ones that came in online, and then we'll see if I see similar things here. Ooh, yep, one of them. Ooh, traffic problems. That's an interesting one. Damn it. Wonder if this all depends on who you happen to have, or there's another, or That is it. Hmm. What's interesting to me, I mean, I'm seeing a lot of things about vectors and matrices, but I would say that the thing that showed up most often is RREF, which had I not looked at 551 materials before coming in here this morning, I would not have remembered what RREF stood for. What does it stand for? It would appear that that was definitely emphasized in a previous course. Uh, I had a linear algebra course way back when I was, I think I was a sophomore, or maybe I had it because I had all calc done in high school, which was a curse and a blessing. One, it gives you a lot of credits going in, so you get to choose classes, all that crap. But it also puts you at a disadvantage because then you take differential equations your first semester and you have zero context for what differential equations are for, right? And you're probably seeing something similar to that in your courses. Like for those who got all the way through and had me in reactor theory. Of course, you're back here, and it's a strange system with this new program. But my understanding was many of you were seeing differential equations for the first time in a long time, or at least you were being required to solve them for the first time in a long time. You might see them in other classes, and that's I think a shortcoming of maybe or the curriculum in general, not just here, but in general, in engineering and technical sciences, will often have you do all the math first, and then we never hold you accountable for it until you get that one lone guy who teaches reactor theory or something like that. So hopefully this course gives us a way to maybe help out with that apparent gap. But thinking back to that course that I had, tell you, I got a B. So I don't think I got an A, B. We didn't have minuses, but we had the center grade. I got a B, and what do I remember? I remember the term column space and row space. I don't even know that I would have been able to muster a null space after all that. But I had all these esoteric terms and not a whole lot of practical know-how. Right? I think that class showed me a little bit on the use of MATLAB for dealing with matrices. MATLAB's a beautiful language, and I might introduce its syntax as part of this just because it is such a natural way to deal with matrices. I mean, the primary language that we've adopted here, of course, is Python, but who's used MATLAB? Right, you probably in that course, and then if you happen to have controls in our curriculum, you'll use it. So MATLAB is great. MATLAB's also not free. You have access to it as a student, and the student version is not super expensive. There is an open source language called Octave that implements most of the basic MATLAB things. So if you know how to set up a matrix and solve a matrix system in MATLAB, then you can do it in Octave as well. But doing it in Python with NumPy is also not so bad. But what I'm trying to do, and you're gonna, this is probably gonna be the hardest part of the course for me to teach. Monte Carlo is straightforward because I give you an application and we can go to town on it. With linear algebra, it's like, yeah, I could write down matrix notation. I could tell you all about these spaces. But my goal here is to help me figure out what we need to have in this class to make sure that you leave it knowing how to use matrices. Maybe those of you who wrote down the reduced row echelon form, like that, maybe that's stuck and you could take matrix systems and do everything you need to do with them. Maybe you got what you needed out of that class. If it's anything like me, you just remembered a term and maybe you weren't able to do much with it. So we'll see how that goes. Right. So bear with me. Given that you've already had matrix theory, I feel like I can't do any damage to you, right? You know what you know, but I'm hoping that we can have a good time and help piece together a story, as it were. I'm very much about this is the hardest thing. Like I've spent hours on this material, and yet I don't actually have that much prepared because I want to find the story. I want to find the right way to take you through this material because this is a non-standard course, right? This course is in a sense supposed to be a supporting course, just like ME 400 was. And I've told you before how much time I spent on that course. It is hard to put together these courses that are primarily the tools that go into a toolbox when you're not building a house, right? It's hard for me to teach you how to frame if you're not framing something, if that makes sense. Okay, so we need you'll get the tools. You'll know how to use the Sawzall and the miter saw and all these other things, but we've got to find the house to build, as it were. All right, so what we're going to use for that house actually goes all the way back to our first day in Monte Carlo. We're going to take our Monte Carlo model with the fixed neutron step. I'm going to modify the way that we set it up a little bit so that it maps on a little bit more naturally to the matrix form, but you'll recognize what we're doing. Okay. Turns out that what we do will also work for cases that are not as simple as that, and possibly even, well, we wouldn't be able to treat the newest version of your simulation where you have free flight paths without doing some additional stuff. But if we start off with this fixed step, we'll get to a set of equations that will actually give us a way to go into two areas of math. One, the one that we're starting is all the stuff about matrix equations, linear systems. The other thing is if we take certain limits, we're going to get ourselves to differential equations, right? Which is the other branch of math that we care about. You've all had differential equations too, right? So, huh? No? Yay? Okay. Yeah. All right. So, kind of breaking the ice to give us a sort of a signpost to where we're going. Let's suppose that we have the spectrum U with elements U1, U2 through UN minus 1. What does this T stand for? Right. So in this case, I'm going to use matrix notation. Now, in theory, you haven't had, or at least this course is set up so that you haven't had the matrix theory class. But out of curiosity, Is Math 551 the first place where you learned what a vector was or what a matrix was?
Maybe the vector didn't come down.
You've seen the vectors before, right? Well, so what this is a vector, and a vector is really nothing more than a couple of values. What does a couple mean? Sequence, ordered sequence. Okay. The notation is to use square brackets. The T is a transpose, which means that we should actually be viewing this thing as a column of values. Now, if you look at the structure of this thing here that I'm calling A, that actually looks like a bunch of columns, or you could think of it as a bunch of rows, but it's the same idea as the vector. Right? It's multiple vectors arranged side by side. Okay, and then we have this matrix and the vector u, and that's all set equal to b. And what's not shown here explicitly is the fact that this is a times u. So it's the matrix times the vector is equal to this other vector. Right? So this, of course, is a linear system. And I haven't put the sizes here, but A is square, meaning it has the same number of rows as columns, and that is equal to the number of elements of U. So when I write this equation down, why would it be the case that each row involves only the name? What do I mean by that? Well, if I take a look at each row of this matrix A, you'll notice that at most there are 3 non-zero values. The rest of them are zero. Okay. So what would give rise to that sort of structure? Then on the right-hand side, this vector B, which we can think of as a forcing function, or we could call it the inhomogeneous term. We could certainly call it the right-hand side of the equation. Why would this only have a non-zero in the last entry? And then what might these U elements represent? Obviously, where we're headed is the use of this matrix system to represent what we've been doing all along, which is representing neutrons escaping or getting to a detector, right? So what do you think these could represent? Why would they be only neighbors? Think freely. Be free. With respect to what we've been doing with neutrons walking around, what do you think these U could be? What are possible interpretations? Bins, okay, so it would represent something about the neutrons in some bin. We're actually going to make it super easy, and because the neutrons are going to assume to live only on discrete points, right? Because if they have fixed steps, they're only going to land on these points. We're going to actually limit it to integers here, right? But the integer steps, think of that as just indexing the delta that we had talked about before, right? So we'll get rid of the delta here, just talk about neutrons on individual integer lattice points, right? But what could the U's be that? So when you say binning what? Okay, so it could be something like the collision fraction or something, or the collision number, collision density, right? So you could maybe be let's say the expected number of neutron collisions at a certain point per, right? If you divide by the original number of neutrons. Okay. That's a good guess. It's not quite what U represents here, but we could change it around so that U represents something closer to that. Any other ideas? What was it that we were actually computing in the Monte Carlo simulation? In the very first one, we were computing a response. What was that response? The number of neutrons detected, and then what was
which direction?
So we had to sample that. We had to simulate the birth of the neutron, which direction it would go. If it collides, what collision is it? If it scatters, which direction does it go? So all those little pieces of the puzzle led up to computation of the detector response. That detector response, at least in our simple example, goes by another name more generically, and that's called the escape probability. So in this case, why do I call it the escape probability? Well, if I have a neutron that is, let's say that this for this row, we've got a first location, a second location, whatever. We were looking at what's the probability that I drop a neutron at the first location, right? And that it makes it out the right-hand side, right? So it's an escape probability. The probability that if a neutron is here at this location, it escapes over here at this other location. Now, when we added in absorption throughout the medium, that it complicated things a little bit. So for now, let's assume that there is no absorption. The only way that neutrons are lost is if it escapes out the detector side or the other side. Okay, so what these U's will actually represent is that escape problem. So U0 is going to be equal to the probability of the neutron going from node 0 to node n. And actually, for us, that's going to be set equal to 0. We're going to assume that if it lands at node 0, it is 0, which means that node 1 will actually be our starting point, right? We want to know if we drop it in node 1, what's the probability that it gets all the way over to node n? Because if it scatters to the left to node 0, that's equivalent to having leaked, right? So if it hits node 0, it's done. So we have to just shift the indices a little bit to get it into the system. But that is what our U's are going to represent. If I can move along here. Okay. So what we're going to model explicitly are these neutron walks on the integer sites 0, 1, 2, all the way through n. So 0 here, if a neutron ends up here, it's gone. Because we are discretizing it, this is equivalent to our sort of continuous model that we started with, where if we put in neutrons at the left boundary, and if they went to the left, they were escaped. So now, if we drop a neutron here, if it goes to the left, that's effectively like it's gone through the left boundary. So if it goes to the right, it gets closer to the detector at location n. And we can view this as a time step, because we know that if a neutron starts off at one location, for it to jump a certain distance, this fixed distance requires a certain fixed time, right? So we can actually index the neutron's life with two things. We're not going to use those, but it'll be at a location I at time index k, and then k plus 1, it'll be at I plus 1 or I minus 1, right? So you can imagine in time, the neutron will go. So you can either think of it as the number of collisions or the number of time steps. Either one would be totally fine. So sites 0 and n are the absorbing boundaries, and we only care about the neutrons that make it to sites n. Right? So what we want to do is understand what that escape probability is at any interior site I. The one that we were computing in class was starting at I equal 1. All right, that's effectively what we had done before. So the thing that we're trying to estimate is the probability that we hit n before 0. Well, that makes sense? That is the probability that we are trying to do. And in this case, the random variable is our initial location. That's the x0, and that is going to be the ith node. Right? So this is going to be what we compute the so-called escape probability, or what we had called the detector response in the previous modeling. Now, why would we need linear algebra for this? We've done a pretty darn good job using just random numbers, a little bit of intuition, and some guidance from me to put some of the structure together. But a good reason for going to something like linear algebra. What about if we need well-established accuracy? Now, we know that Monte Carlo can give us really accurate results, but how does that accuracy depend on the number of trials that we use?
1 over the square root
of n. Yeah, so if n in this case is the number of trials, then we would need to do the number of trials that we need to do to get a certain precision will grow as the precision the accuracy goes down as 1 over the square root of n, right? So if you want to reduce the accuracy or increase the accuracy by a factor of 10, you have to increase the number of trials by a factor of 100. Right? So that kills Monte Carlo in many cases. There are applications where that square root problem goes away, and that's usually in the case of really high dimensional stuff where there's just no way that a deterministic approach would be able to solve it. But still, you will always suffer that 1 over square root of n. Now notice here, I thought about changing this. I've actually switched n to be the number of sites. The reason for that is the number of sites is going to turn out to be the number of columns that we have in the matrix. I'm going to stick with the normal m rows by n columns. So I'll try to tidy up the notation if I find things that are kind of confusing. Okay? So for our Monte Carlo simulation, we need to use many trials. Now, the other thing that we compute or didn't compute is that probability for every single location. Remember, our Monte Carlo simulation, we chose one starting location, right? The left-hand side of this material. Okay. What if I wanted the same, or let's say the detector response for any starting position, right? Suppose I had something that was, I don't know, variable, or I had a source term that was not just a point source. What if I actually had a uniform source? Well, I could estimate the detector response averaged over all of those, right? Just by sampling. Okay. But what if I wanted individually the probability that a neutron born at I equal 1 or I equal 2 makes it to the right-hand side? I would have to do over and over again my Monte Carlo simulation. Totally fine, I can do it, but coupled with this issue of square root of n, that might be the wrong way to approach it. Okay, so what can we do to get all of these at once? And then what if we have probabilities that change with space? So remember, we've made an assumption, because it made the problem a little easier to solve, that every location had the same probability of scatter versus absorption, or at every location, the probability a neutron was scattered to the left or to the right was constant or uniform. What if all those numbers changed as a function of I? What if it became much more likely for a neutron to scatter backward or something as you go from the right to left? How would you handle that with the Monte Carlo? Well, you'd have to go through and adjust all of your probabilities, right? All the sampling routines that you do. It's totally doable, but it also makes it more complicated, right? And when you put that in with the other issues, it might make sense to find U deterministically, right? Monte Carlo had a place, a great way to learn, and it's a great way to build intuition and check your work, right? I've used Monte Carlo sometimes just to make sure that the number I get when I solve an equation deterministically is of the right order of magnitude, etc. So what we want to do is derive equations that let us compute these escape probabilities deterministically. And those equations it gives us this nice starting point for branching off into the linear algebra stuff that we're going to do now, and then some of the differential equations that we'll see later on, right? And I'll try to tie it all together as well as possible. So just to review that simulation that we did, here's some pseudocode. Now I've simplified it from what we had before to focus only on the application that we care about, getting to n. So this is for the pure scattering piece. So we first set the position, right? We get this random, we choose I, set that for our position. Now, while the position of the neutron is not at 0 or n, so meaning it's in one of the interior locations, so I equal 1 through I equal n minus 1, we'll step to the left or the right with equal probability, right? That's the same thing that we had done before, okay? Then, by the time when that while loop breaks, meaning that we actually got to 0 or n, we make the count if we got 10. Otherwise, we're stuck, right? It's the same loop that we did before, it's just in a nice compact form here. So the estimate for UI is going to be the fractions files at n. Okay? Again, this is Monte Carlo, and the limit here is we are getting an estimate for just one location I. We chose this I, right? So we get the response or the escape fraction for that one location. So we'll always be able to use this Monte Carlo routine as a sanity check. Okay, so here is that implemented in code, right? So it's a very short, we're going to get rid of, oh, that's weird. You see that too? That is bizarre. All right, so anyway, you might remember that if we have 4 locations, right, not including the I equals 0, right? Then if we start at that first location, the fraction for the pure scattering case was 1 over n. It's about 25%. Do you remember that from earlier? Okay. we're gonna actually go through and see what that analytic solution is as well for this case, right? But just know that this estimated escape probability is almost identical to the run simulation that we had done before. Now, to get the relationship for for this random walk, we need to establish a recursion. So what we are actually trying to compute is UI. Remember, tell me, make sure we're on the same page. What is UI? Yes, so you drop a neutron at location I, what's the probability that it ultimately gets there? Okay, so the escape probability, we can actually relate it for one cell to the ones at the neighboring cells. The reason for this is if I am at cell I minus 1, the probability I get to cell I is what? What's that? 50%, right? Because it's purely scattering. I will always have a collision, and that collision is always going to be a scatter here. Things will be a little different if we change that from pure scattering. Then we'd have, instead of 1/2, we'd have C over 2, right? But C is 1 for the pure scattering case. Okay, so the probability that I get from that I'm dropped at point I and I make it all the way to point N should relate somehow to the probability that I'm dropped at the left neighbor and the right neighbor. The reason for that is if I'm dropped at the left neighbor, there's a 50% chance that I step to the right. Right. So the ways that I get to this location in the first place are conditioned on where I was. So half the time that I'm to the left, I'm going to make it go, and then half the time I'm to the right, I'm going to be scattered. And so the probability that I am at either one of these points and then make it here is given by here by the half. And this should therefore be the probability that I get to the final endpoint, having already been at either one of these points. So you have to be at one of these points in order to start off that I in the first place. Okay. Does this statement make sense to you? Does it seem plausible? I think if I wanted to formally prove it a little bit more, we'd have to talk about expectation again. But if we agree with this, at least at a heuristic level, we can move on and do some cool stuff with it. Any reason to think that this doesn't work out? Okay, so that is a recursion relationship for the probabilities, and you might actually represent or think of it as a different kind of equation. Anybody know what this sort of equation is? It's a recursion equation, but there's actually a different kind of equation that this is known as, or a different family. It's a difference equation, right? Because what we get is the relationship at one cell as a function of its neighboring cells. So we can move this around and we'll get subtraction signs and so forth, but this ends up actually being a second order difference equation, which if you hear the word second order, what else comes to yeah, exactly. And we're going to find out that this second order difference equation ends up looking a lot like a second order differential equation, right? So it's a second difference equation because it's a relationship between one cell and two other pieces of information, two neighbors, it's left and right. So it's a central difference expression that we'll get. Okay, so these are discrete, and this establishes the relationship for I greater than or equal to 1 or less than or equal to n minus 1, but we still need to define something at those boundaries. So if I set the probability that a neutron landing at cell 0 is 0, that is effectively the same thing that I did in the original simulation, where if a neutron ends up to the left of the left boundary, it's gone forever. So the only way that I can get to cell 0 is, well, how do I get to cell 0? Where do I have to be first? I could either drop it at 0, in which case it's done, but if the neutron is walking around, where's the only place it can start at where it lands here? Cell 1, right? So if I drop a neutron in cell 1, that's what I was doing in the original simulation, saying I dropped it at x equals 0. That effectively is what you wanted. When that thing moves to the left, it has left the building. So I can just define a new node saying if it lands here, it's gone. It's the same thing, right? It represents the same outcome. And then if I get all the way to cell n, what does this equality tell us? If the neutron gets to cell n, what's the probability that it gets to cell n? It's 100%, right? So these are boundary conditions. So we actually have a set of equations that relate triplets of u's with additional constraints at either end. If you remember differential equations, this is the exact sort of thing that you need to solve a 2-point boundary value problem, which I know is not something that you cover a lot in Math 340, but if you've had reactor theory, you'll see that a lot. So this will be sort of a first place for students in the nuclear curriculum to get an idea of boundary conditions and what they represent physically. So we can rearrange the recursion relationship, right, that we had here. We multiply it by 2, right, and then we bring terms to one side to get this. So this is the form that should suggest difference equation. Right? It starts off as this recursion equation, but when we write it in this form, we see 2 differences from the neighbors, and then this factor of 2 times the cell value itself. This being equal to 0 is a second difference. And if we want to think about curvature, so this is for discrete things. If I'm talking about a continuous function and I turn the word second difference to second derivative, what function goes to 0? If I have a function of x, so remember these points I represent 3 points along the x-axis, right? So if you view this as a function defined on x, and this would be its second derivative, what sort of function has a second derivative that vanishes? Quadratic. Linear. Yeah, quadratic, you get the baseline and then you get a constant left over. But if you are a linear function, the second derivative wipes you out. It's the same thing for these discrete problems. So the second difference equation has a discrete curvature, and that discrete curvature would give us 0, which means that what kind of function of I do you think the solution is? Linear. Yeah, so it will be linear, which should start to make you think about that reference solution I gave you. I remember for n equal 4, we had 25% escape. If I turn that to n equal 5, we'll find 20% escape. There's some sort of linear relationship here, and it's suggested exactly by this equation. So because of the symmetry, right, because this is minus ui minus 1 and this is minus ui plus 1, there's no net bias, meaning that there is no anisotropy in the scatter. We're assuming equal. We can account for all that stuff. It's just the equations get more complicated. Okay. All right, so the first thing that we're going to do to turn this discrete system into the form that we care about now, which is vectors and matrices, we're going to take all of these unknown probabilities and stack them into this vector u. Now, why don't I have u0 and un? They're known. Now, I could put them into this and still have a totally fine system, but this is a kind of a common way to do it. And by eliminating the u0 and the un, we'll end up with a matrix that has a very that it represents a very important matrix. And in fact, it's one of the matrices that shows up in the where does it show up? Almost right away in the string notes. Well, I'll point that out when we get to there. Okay. So for each interior index I, we can write one equation. So for I equal 1, we get this difference equation. The right-hand side is 0 because the u0 is set to 0. That's one of our boundary conditions. Okay. So we could have put u0 here and then had I equals 0 and then u0 equals 0, but we don't need to keep that explicit. Okay. So I equal 1, we get to substitute one of the values, but then for I equal 2, 3, 4, all the way through the second to last equation, it'll just be a repeat of this structure. And then for the very last equation, we get this structure because we know what that value of UN is. And when you put it all together, you get A times U equal B. And it's a specific kind of matrix that we get. It's called a tridiagonal matrix. Uh-oh. I knew I missed one of them. What's up with my keyboard? No. Why is that? I think this. Sorry. Apple A. Yep. All right, so this is what we get for that final setup. This is a super important matrix, and it's kind of funny. So I had the distinct pleasure back in my first year in the PhD program to have a class with Bill Stray. He's the one whose notes that you see. He's written lots of books, and he was such a big fan of this matrix. He also turned, I think, 80 that year, and so the class, I wasn't part of it, but I was in the class. There were a bunch of brown nosers. They baked cupcakes and brought in a big tray of cupcakes. That was this matrix, so a bunch of zeros with 2 down the diagonal and then -1. He was just incredibly taken aback by it. Anyway, had a nice story. All right, so we get this matrix. It has a number of features. One is that it is sparse. In fact, I think I'll keep it up there, okay? I actually saw in your responses that some of you had written sparse, which is neat. I'm not sure that you would have focused too much on sparse matrices in that class, but it's something that we can talk about in here, and it's something that I highlight in 701 when we have to deal with very large matrix systems, okay? But this is a sparse system, meaning that most of the matrix itself is filled with 0, right? Anytime you have a matrix that is full of zeros, you call it sparse, and you probably look for special ways to treat it, right? Rather than just using, you don't waste your time putting it into row echelon form, inverted, that there's others. Okay. All of the coupling between the unknowns is local, right? You only have one cell relating to its neighboring cells, immediate neighbor. Okay. And then the boundary forcing shows up on the right-hand side in the forcing function B. And that has only one non-zero value because the only thing that we put in the right-hand side was the condition 1 at the very end, right? So we see the 1 here. And in a sense, what this is telling us is we are forcing the system to have a response here. And that's what we're going to be computing, the contribution from every one of those points to the right-hand side detector response. All right. So a couple ways to look at matrices. One is based on the row picture. This is kind of where the physics lives. This is the way that we construct matrices. I'll tell you that when we solve matrix systems, this is not necessarily the best way to look at it. But it is an important way to look at it when we are actually constructing the matrix in the first place from the physics. All right, so this is a balance law at node I, right, for the ith row of AU equal B. Now, for most of those rows, BI is equal to 0, but you could imagine each row be perturbed or forced by some value, okay? So because we only depend on nearest neighbors, the whole model itself is called local. And it's for this reason that tridiagonal matrices show up almost everywhere, right, in the physics. You get it when we have diffusion and conduction discretizations. You get it when you take the resistor networks you study in ECE 519. You all remember that fondly, right? You know how to set things up, right? So resistor networks, it can often be set up in tridiagonal form. And then, of course, we have our random walk, which, of course, random walks are intimately related to diffusion processes, so maybe not too surprising. The other way, and this is one of the key things that I got out of Strange material, is rather than viewing A U equal B as this set of rows, these individual balances, you can actually take this and view it as the sum of the columns of A, right? So if I have this matrix system A U equal B, that left-hand side, the matrix times the vector, I'm sure you remember matrix vector, and you might remember the algorithm you used to compute it. In fact, does anybody care to share how you would have done A times U? If I give you a matrix A, like we just had, and I gave you a vector U of some values, how would you compute A times U?
Multiply corresponding rows and columns.
Yeah, you take a row of A and multiply it by U, right? Element wise, and then you sum them up. It's a dot product. Does that ring a bell? Okay. What this is saying is there's a different way that you can compute that. You can actually just take each element of U, right? The first element, multiply it by the first column of A. And then you can add this second element of U times the second column of A. So all of this ends up being a combination of the columns of A. Why does this matter? Well, if you have a linear system, AU equal B, what must be B? It must be a combination of the columns of A, right? And in fact, that set of combinations of the columns of A, all of the combinations of A that we get, has a special name. Many of you wrote it down. What is that called? What is this? What do we get when we consider every possible combination of the columns of A? What do we call that?
Vector space.
Huh?
Vector space.
It is a vector space where those vectors are the columns of A, but it has a special, what are these? They're the what of A? And so what's the space? The column space, right? You just have to read. Okay, so if you heard the term column space, I sure did when I was a student. But that's fine, yeah, all the combinations of the column space, but what wasn't pointed out quite easily or straightforwardly is the fact that if I have a system A equal B, for it to have a solution requires that this B can be represented as the combination of the columns of A, right? And that combination that you need has to be defined in this U, right? The weights of all those columns of A in order to get B have to be defined in U. If you can't do that, then you don't have a solution. Right? If this thing is outside of the column space of A, right? And what's outside the column space of A? I think somebody else wrote that. What are the spaces that you remember? Column space, or row space?
Null space.
Null space. What's the null space? It's the space of the things that aren't contained in the other space. So the null space of A is all those things that don't live in the column space of A, right? So if I can't solve this, if there is no set of numbers U such that A times U is equal to B, then B has at least some part of it that lives in the null space of A, right? So there's a reason for having all these terms. I don't expect the terms to have had any real meaning to you up until this point, but I'm hoping to give you a little bit more ammunition with those terms as we go along. So in other words, we need that right-hand side to live in the column space of A. And things like the reduced row echelon form and elimination more generally are tools for figuring out if that is true or not, right? That is ultimately what those algorithms are intended to do. Okay, so we can get all of those interior probabilities, all those escape probabilities with one solution of the system, right? And then we can compare that to the Monte Carlo estimate that we get for a selected I, and then we can actually compare it to the closed form solution that we get from something called an ansatz. Anybody hear of this term before, ansatz? I think it's German. It's like guess. Right? If I say what, you remind me, when we have a second order differential equation, constant coefficients, what do we plug in to that equation to get a solution? Anybody remember? No harm if you don't. Some of you have seen it more recently than others. Well, keep it to yourself. We'll see what it looks like for the discrete case here. Okay, so here is a little code, right, that you'll be able to, I have not put the homework notebook together yet, but I'll get that ready today. So you'll be doing some small exercises based on what we do in here today, right? This is a function that solves the tridiagonal system for n points. Okay, so just walking through, of course, we get, we'll define m as n minus 1. We'll initialize that matrix A. We'll initialize the right-hand side B. And then for every row in the corresponding range, we'll put the 2 on the center diagonal and we'll put the minus 1s above and below that diagonal. We'll only put a 1 in the very last element of B. If you don't remember from maybe lecture 3 or 4, one way that you can get the last element of an array in Python is to use -1. So -1 will say, hey, starting from the right, take the first element. So -2 is actually 2 from the right. So forth. So you can actually reverse your indexing. This will return that the set of matrices A and B. And then what we get for n equal 4, we build it. The way to solve a system using Python, at least with NumPy arrays, is that you np then elch.solve. Right? Next time we'll figure out what solve is doing, but know that it's effectively doing Gaussian elimination. We'll dive in and review that algorithm because it's one of the, even from a programming standpoint, being able to implement elimination is a good good exercise for your logic skills. Right? So I expect you to use and be able to use a built-in solver like this, given the matrix A and B, but we will see what goes on under the hood, I believe next time. Okay. So here's the closed form. You remember that solution, right? 1 over n. And so in this case, because we chose n is equal to 4, that should give us 1 over n, 2 over n, 3 over n, 4 over n. So everything that we've been looking at. Okay. And then we can compare it to 1 point from the Monte Carlo. So in this case, I am setting I0 equal 1. I'm getting u hat. You remember my use of hat as like an estimator? I think I used that before. And so in this case, I could set the seed and then we can run all of them and see what we get. And let's see. This is my exact solution from the linear algebra. This is my exact reference solution. And here's my Monte Carlo solution. Does it seem consistent? Right? I guess we all take a leap of faith that this is the correct thing, but I believe the setup of this equation, and we've already beat this one to death, right? So I feel pretty comfortable that we've gotten what we want. Okay. Then if I take a look at that escape probability for the linear solve and then the closed form, of course, they land right on top of each other, right? Because there's there's really no error in the solution of that linear system. All right, so here's that ansatz solution, which is really, it stands for guess, and that guess comes either from physical intuition or mathematical know-how. So we have this interior recursion, okay? Just like we do in differential equations, we can assume an exponential ansatz, right? We can assume that our unknown u is equal to some power function. Sometimes we might do e to the r for, right, like e to the r x if it's for a second order differential equation x, but ultimately often always a power. Okay, so when we do that, we get this equation here, and then that gives us an equation for the two possible roots r. In this case, we have a repeated root r equal 1, and so that gives us a solution that looks like this. Now, why would we have this solution? Why would we have the two terms a and b? How does this follow? Do you remember in second order differential equations when you have repeated roots? There's a trick. For instance, if I have a repeated root in, if I have a second order let's see if I can come up with, I don't think I can come up with a repeated root one off the top of my head, but often you'll get something and then you'll like, so suppose I have one solution that would be e to the RT. If R is a repeated root, you might remember that you have to try e to the RT, does that, in order to have two linearly independent solutions. So that would be effectively what we're seeing here, right? Just in order to have these two. Okay, so once we get that, then we can apply the boundaries, and lo and behold, we get that U is equal to I over N, which is what I had claimed several times ago. Okay. This same thing is doable if we had a scattering ratio that was not equal to 1, right? So instead of the 1/2 or the 2 here, we would have something that has a C in it. I might leave that one for the homework, right? But I'll give you the ansatz, you plug it in, and you'll work through and get something that's satisfying, I think. Okay. So why bother with the matrix if we know how to compute this sort of analytically without touching matrix? Okay. If we change the physics, this thing might not be so easy. It's reasonably easy, even if you have C not equal to 1, but the minute you start adding anisotropic things like, the chance that it scatters the right is no longer uniform, then I don't know that there's going to be an easy analytic solution, right? There are a lot of papers out there that I've seen on random walks with absorption. It gets pretty hairy, right? So if we want something that is straightforward, the matrix approach is actually the right one, okay? So if we were instances that would change physics, the bias walk, if we had things that changed as a function of space. And then when we go to higher dimensions, things get real wild. How do you do a random walk when you have a 2D grid? I mean, you could do it, but things get, I wouldn't want to write out that recursion relation. Okay. So in this case, as long as we can define the physics, the setup is essentially the same. We just we'll have something that changes every time we make a new row. So what you should remember, balance laws that we have from physics will lead to some sort of recursion on the individual points. And then that will lead to a set of linear equations that when stacked gives us AX equal B. And so this is sort of one place that we get the matrices in the first place. And then once we actually get the matrix, we can look at how it is constructed by looking at rows. But as we'll find, and we'll hit on this even more next time, the column picture, this idea of the combination of the columns of A as being where the solution lives is so fundamental. Okay, so that's everything that I wanted to talk about today, and I think that actually gets us well into diving into elimination next time. So we've got just about 12 minutes left. Any questions that you have on this material in general or on the project? Yeah.
For the project, do you want us, are we allowed to change the, I guess, the required number of inputs for any of the functions, or can one of those same?
What are you thinking you'd want to change?
Well, I just had brought in M into one of the functions that is already having.
And that's not something that was inferable from like a length of an array somewhere?
Well, you can infer it from the bin, and I just.
Yeah, I wouldn't change the signature. I think they're set up in a way, so if you need to get M by doing a length all inside the function, that's totally fine. But that's like that's actually good, because if you think about it, by every time that you can use a piece of data to encapsulate the information you need, the better. Because if you put in that argument, so to put in M, that becomes a redundant argument, right? And anytime you have redundancy, you increase the chance of bugs. and it'll probably break my grading system. But that's probably the most important. Yeah, so good call. Certainly, if you find things, like this is all new material. So if you see things in the code that you think would be like if you think I did something that was kind of dumb, let me know, and it might be that I need to refactor some of the example code too. I don't think so in this case because I went through it and it seemed pretty okay. But if anytime that you see something that's just seemed like, I don't think this is right, let me know. I might have gotten it wrong. Yeah.
Where's that, do you have on Canvas the file for the code that you did for the example for the neutrons being born?
Lecture 7? Yeah.
Lecture 7? Yes.
Yeah. Any other materials that you think I should have put up that I just forgot? I think I've been pretty good about it so far.
The test file, or do you want to think
The
the test file you mentioned last lecture?
that's uploaded.
Oh, it is.
I uploaded that in class. Right toward the end, I had it mostly ready. I just had to change a couple of things before uploading. But yeah, you should have had that before the end of class last time. So use that, add to it. But if you make sure yours runs with that, because that has some basic sanity checks that'll make sure that you haven't done something to break the system. So if it runs with that, it should run with the rest. Because all I did was take my full set of tests and I deleted some of them. Right, so it should be pretty straightforward. All right, do I have comments or questions here?
Can we default the inputs to the functions?
All right. Our reduced row echelon form was what we spent 80% of matrix theory talking about. Interesting. That's too bad. All right. Well, if there are no other questions, you are free to take. Oh, wait, did you just ask it? Yeah, sorry.
Can we default the inputs to the functions just for debug? Like I have a separate file I'm using for debugging.
Mm-hmm.
And so I've been defaulting the inputs to the functions so I don't have to have a bunch of extra lines in the debugging file.
That might be fine. I don't think. So you've changed some of the starter code.
Yes.
I think that's okay. I can't promise.
Okay.
I'm like 80% sure that won't cause you issues, but I mean, at the end of the day, in the testing side, is it that much harder to put these fixed inputs? Because like, isn't that what you want to be testing for? Is like, because if you do tests that then rely on default values, what if those default values change? Then your tests break, which is that's what tests are for. They're meant to break so that you fix what you did. So just be careful. Okay. Yeah.
When will this merge to do?
This one, assuming I can get it out before the end of office hours, it would be Sunday.
Okay.
Yeah. And if not, then I'll push it to next week. But I think I'll get it out. I don't want it to be too long. I just want you to kind of play around with some of the material that we talked about. So, all right, that is everything. I will see you all on Tuesday.